Okay, let's see how do we apply this, okay, and see some of the limitations of this theorem. Okay, consider this function, the absolute value of x times 1 minus x, which is, in other words, x1 minus x, whenever this thing is positive. Okay, let me plot this. X times 1 minus x is this parabola, right, which crosses the x-axis at 0 and 1. Okay, this is x times 1 minus x. So it is going to be positive when x is between 0 and 1. Okay, and it's going to be negative, so that we can say this is x times x minus 1 when x is greater than 1 or x is smaller than 0, right? So that means if this is negative, the argument is negative, then the absolute value of that is minus this. Okay, that's what we know about the absolute value. Now, well, if this is the function, let me plot the absolute value of that function. The absolute value will make this be the same, right? And then for the negative part, it would be the same thing but mirrored against the x-axis. Okay, so this is the absolute value of x times 1 minus x. Okay, so let's see what are the extrema of this function. Okay, in order to do that, we compute the derivative of this function. Okay, and so the derivative of this in the in both sides, this is just 1 minus 2x, and this is 2x minus 1. This is valid when x is between 0 and 1, and this is valid when x is greater than 1 or smaller than 0, but we don't know if it's valid in the limit, in the point when these two functions join together. Okay, so we don't know if the function is differentiable at 0 and at 1. Okay, and that's what we're going to see. So the limit when x goes to 0 from the left, okay, of f of x plus f of x minus f of 0 divided by x minus 0, right? From the left, f of x is going to be this. So this is the limit when x goes to 0 on the left of x divided by x minus 1. F at 0 is going to be 0, right? And this is divided by x. So the limit of this is this and this cancel out. This x minus 1, when x goes to 0, this is minus 1. Okay, and you see, right, when you go from the left, this function, the slope of this is negative 1, right? Now, if you compute the limit when you go from to 0 from the right, it's now the limit when you go to 0 from the right of this function, x times 1 minus x, again divided by x. The result is 1, because you see that the slope when you come from the right is positive 1, right? So there's f is not differentiable at x equals 0, and a similar argument will give us the same thing at 1. Okay, so the function is not differentiable at 0 or at 1. Okay, now let's find the points at which the derivative is 0, right? So f prime equals 0 where? So first of all, the first derivative, 1 minus 2x equals 0, this implies that x has to be 1/2. Okay, and at 1/2 we have this point, which is the maximum of the function. Okay, so that corresponds to what we expect from the theorem, right? The function has a maximum at 1/2, right? We can see it here, and because the function is differentiable in this point, then this derivative is 0, right? If we try to find the 0 of this, we get the same thing, but in this case it doesn't work because x, so there's no value that makes the derivative 0. Sorry, this is wrong. It's not f prime material. It's f equals 0. Right, sorry. So what I was saying is that there is no value 2x minus that makes this derivative equal to 0 in this interval. Okay, so in the interval that x greater than 1 or x smaller than 1, the function, the derivative is never 0. Okay, so does that mean that this is the only extrema of the function? Well, no, it's not. Okay, as you can see, the value of the function at 0 and 1, which is 0, right? The f at 0 is equal to f at 1, which is 0, are absolute minima, right? Because these 2 points, well, they're local, but both of them are absolute minimum. Every other value of this function is positive, right? If they're not 0, these are the only 2 zeros of the function. Every other point in the domain will give you a positive value. So these 2 are minimum of the function, but we didn't find that the derivative at these points was 0 because the derivative at 0 and 1 doesn't exist, okay, as we have seen before. Okay, so that means that we have to be very careful when applying this theorem to find extrema, because sometimes we need to check also the points where the function is not differentiable. Okay, and so yeah, in order to find the extrema of a function, we need to check the values that make the derivative be 0, but also the points where the derivative doesn't exist. Okay.